Hello everyone, today we're going to go over the LP sequence space in functional analysis. This is a pretty abstract space, but after the end of this video, I'm sure that you guys will appreciate what this space entails and applies to. So without any more further ado, let's begin. So what is an LP space? Well, an LP space is defined as a set of sequences. We have x1, x2, x3, all the way to xl, where L can be a natural number, or it could be infinity. Xn can be a real number or a complex number. And the most important part, the summation, the sum of n equals 1 to L of, I believe it's xn to the p must converge. And that is the definition of an LP sequence space. There's an LP function space, but in this video we are going to cover the sequence space. So this definition may seem a bit abstract, a bit convoluted, and it is, but it's not really hard to understand once we break down each part. So first of all, let's break down the left-hand side. So the left-hand side just says that we have a set of sets. So we have like y equals y1, y2, y3, all the way to y small l. You have like m equals m1, m2, m3, all the way to ml. You have like k equals k1, k2, k3, all the way to k small l. And we just have this set of all of these sets. So we have a set of sets, and each member of the LP space will be a single set. So we have a set of sets. This just goes on. We have a set of sets. Okay? And this is just a single set. That's what this LP space is referencing. It's a single set. Each member is a single set, and the entire LP space is a set of sets. Okay, so this right-hand side is just our conditions on each member of the LP space. It's a condition on each of these sets. So first of all, L is a member of the natural numbers, or it's infinite. This is saying that it's basically saying that our set can be finite or infinite. If L is an integer, that means that this set ends after some integer. If it's infinite, then it means that this set goes on and on forever, which it can do. Xn is a member of the real numbers or the complex numbers. Now, if xn is a member of the real numbers, we have an LP, a real LP space. If xn is a member of the complex numbers, we then have a complex LP space. In this video, I'll be dealing with the real LP space for simplicity, but the same concepts carry over to the complex LP space. And here's the juicy part of the meat. We have this is what makes LP. It says that the sum of xn to the p has to converge, and p, by the way, can be any real number. I believe maybe a natural number, but I think any real number, any positive real number maybe. But this has to converge. Okay. And yeah, if these properties are obeyed, we have an LP space. So let me give you guys one example of a member of the LP space. Say we have x equals 5, 3, 4. You can see that this set x is a member of an LP space, since each member of the x is real, and this holds the sum of n equals 1 to 3 of xn to the p, that's equal to x1 to the p plus x2 to the p plus x3 to the p, which equals 5 to the p plus 3 to the p plus 4 to the p. That is less than infinity for all p, right? You can choose p to be 1, p to be 2, p can be a billion. This will be less than infinity. The sum will converge, since the sum has finite elements. If we had an x that had an infinite number of elements, like in quantum mechanics, the four coefficients of there's an infinite amount generally, we would it would be a bit more tricky to actually prove that they converge, but it can converge even with an infinite number of elements. Just that the elements have to get smaller and smaller and smaller as L increases. But if you want to get to off topic, this set is a member of an LP space. So X is a member of L1, X is a member of L2, X is a member of L100. It's a member of LP for all P. Okay, that's just it in practice. Now, so far I've given you guys what an LP space is, but that's like one half of like the importance of an LP space. The other half is the concept of distance. So we do define a metric on an LP space. That's what makes it a space in the first place. It has a metric imposed on it. So the metric that we impose on the LP space, it's going to be a bit abstract, but you guys are going to see why it is sooner or later. The metric xy equals, this metric is the sum n equals 1 to L of the absolute value of xn minus yn, p 1 over p. And that's the metric that we put on this set. So let's just move all this here. So here's our metric that we put on our set of sets. This metric may seem a bit foreign to you guys. Why is the metric defined in this way? And when I started this whole thing, I was like, why is the metric defined this way? What's the use for it? It's actually it's pretty subtle, but this metric is very powerful that we will see in a moment. So let's just talk about what this metric is saying. So we have an LP space. So we have p could be equal to 1, then this would be 1, and here would be 1. If p equals 2, you'd have a squared here and a whole square root. So let's expand this sum. So x is just x1, x2, x3, all the way to xl. And then y is y1, y2, y3, all the way to yl. Okay, so let's expand this sum to show you guys like what's actually happening. We have the distance between two of these sets. So we're defining the concept of distance between two sets. So it's very important to note that distance in topology, like metric spaces, like just metric spaces really, but distance is in like analysis, it may not really coincide with our usual notion of distance. Like we say, oh, distance between 2 points, but in analysis we kind of generalize this to that with the distance between two sets, where there may not be where there may no longer be an intuitive notion of distance. We have this distances between two functions. We can have all sorts of these that we impose on our space. So we define the distances between two sets, and we do that too in usual Euclidean R2 space. But we have a distance between two sets here, and the distance between two of these sets, x and y, is just going to be this. So what we do here, distance between x and y, is we are going, okay, we have x1 minus y, sorry, let's move that up a bit, x1 minus y1 to the p, plus x2 minus y2 to the p, plus dot 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 xl minus yl to the p. Of course, these would have to have the same order, right? Because it wouldn't make sense to have them different orders of these two, since n these two ends are the same. There has to exist in other words, there has to exist a bijection between these two sets. So, and then we take all of this and put it to the 1/p. And that's what we define as the distances between the two of these sets. Alright? Okay, so again, this might seem a bit like barren approach to defining the metric, but that's how we define it. So now I'm going to show why this metric is so powerful, because this metric, so let's talk about the metric for the L2 space. Let's talk about the L2 space metric for sets that are in R2. Okay. So first of all, the L2 space metric is for L2 ... our metric between two sets is going to be this n equals 1 all the way to L, but it's for R2, and for R2, L is just small l is going to equal 2, right? So you have xn minus yn to the p, but p is just going to be 2. So we have a square root, really. So we have a square root of x1 minus y1 squared plus x2 minus y2 squared. That's our metric. Now recall that for R2 x is just x1 x2 and y is just y1 y2. Now here is where the confusing part happens. So these are two general sets, right? Like this x, this y, these aren't like the coordinate points x and y. They're like let's just draw out our excuse this. This is just chocolate. I was a bit hungry before this, but here is, let's move this a bit more. Here's R2, right? You have the 2 points, like here's x and here's y. Here would be x1, x2, and here would be y1, y2, really. And here x1 would be like the x coordinate, x2 would be like the y coordinate, and here would be like x prime, and here would be like y prime. All right, that's what we really mean here. And so let's actually use these substitutions. Let's replace x1 with x, x2 with y, and these with primes, right? So after doing that, so we replace this with x. This becomes I believe. So what's y? Y1 is an x prime, right? X2 is going to be y. Y2 is y prime. So y prime. So what we have here is that the metric xy is the square root of x minus x prime squared plus y minus y prime squared. And if you guys have ever studied the R2 metric in your life before, you know this is exactly the common R2 metric. It's the metric that we impose on R2 all the time. And that's like why the LP space is so powerful. Because we see the R2 metric is actually just the metric. It's just the LP metric for P equals 2. And we're at small l equals 2. That's just the R2 metric. That's where this metric actually comes from. Now, we can impose any metric we care in R2, but the one that we commonly impose is just the L2 metric for points in R2. That's what it is. And you guys may, if you guys aren't, these are slashes, by the way. These like primes. So you may also see it be written in a bit of a different notation. You may see it be written as like x1 minus x2. Oops, I made a big mistake here. These should be absolute values, not parentheses. Okay, these should be absolute values. My bad. So we have x1 minus x2 squared plus y1 minus y2 squared. These aren't the same as what I wrote here, but sometimes you will see it being written as this. It's this bit of a different notation here. And yeah, that's the metric for R2. So that's why LP space is so powerful, because it gives us the standard metric that we care about for seemingly unrelated spaces. So yeah, that's the R2 metric. Now I'm going to go over vector norms. So the LP sequence space can also describe vectors. So let's just go back to our R2 example. So we have R2, okay, we have that. So here we have 0, 0. Oh, also, this is just the Pythagorean theorem, right? Here's a big X, here's a big Y. So, just saying. So yeah, also, so normally in high school we say, oh, the distances between 2 points is the Pythagorean theorem. But that, there's a bit more nuance there. We can declare the distance between 2 points to be anything we want. In fact, in the derivation of the Pythagorean theorem, which you guys can do yourself, we just declared like c to be the distance, but it doesn't have to be the distance. We can define the distance to be anything. We just define the distance usually in R2 to just be the Pythagorean theorem, because, well, it's very intuitive. We like using right angles, right? So here is R2, and here we have 0, 0. Then here we have, let's call this x, y, small x, small y. We can send this big X and big Y, but who cares? We can draw a vector that connects these 2 points, right? And the length of this vector, vectors are always at the ordinate by definition, right? So the length of this vector, so we have a vector. The length of this vector is just going to be the distance between these 2 points. And the length of the vector is just going to be x squared plus y squared, right? Since these x2, xy, they're both 0, right? So the length of the vector is just going to be x squared plus y squared. And the length of the vector is just the distance. It's just the distance between these 2 points. It's the distance between x, big X really, and big Y, where here's big X and here's big Y, right? So the length of the vector, which we call the norm sometimes, depends on the metric that we imposed. Or we can say that the metric is kind of derived from the norm sometimes. And yeah, this is the length of the vector for in L2. Now, I want to emphasize something here. We may be inclined to say that the norm of the vector is just the square root of the dot product of the vector in itself. Because recall that the dot product, if you have in 2 dimensions, the dot product of a vector in itself is just going to be x squared plus y squared, right? Right. This is the x component of the vector, y component of the vector, and I certainly emphasize that this is only in an orthonormal basis, and a Cartesian one to be a bit more precise. And this is the length, this is the dot product, right? And then we say, okay, this is the dot product, and then the length of the vector, is the square root of this, bam. And usually, in undergrad, we'd be like, oh, okay, this makes intuitive sense, cool. But really, there's a bit of a gap here. So it's not really much that we found. Sorry about that noise. It's not that we found the distance be of the square root of x squared plus y squared. We really just declared that to be the length of the vector. but we could impose any length. In fact, this actually is the length of the vector, but in the L2 level, I think that's how you pronounce it, sequence space. However, if we chose a different sequence space, like say L3, for L3, the length of the vector would, or the norm of the vector would instead be the cubed root of x squared plus y squared. And since we have this p is a 3 now, and L is 2, small l is 2. So we'd have the cubed root. So this is why we, all the time in physics and application, all the time, we usually operate under L2. Since under L2, the length of a vector, the norm of the vector, this is between 2 points, is just the square root of the sum of the components of the vectors once squared. And that's the Pythagorean theorem. That's why we usually choose L2. I'll say it again. To clearly want to emphasize like why we always see L2 in quantum mechanics, Hilbert spaces. That's L2. In computer stuff, we use L2 there as well. So we use L2 because that's when the square root, because like the dot product of a vector, like, we don't define that. It's just like, the dot product, because you didn't know, of a vector in itself is just like this sum over here, where this is the metric tensor components. We don't declare the dot product. This is the general formula. We can't declare the components, but the general formula is the same. We don't declare F equals MA, right? So the dot product is the same. But in L2, it happens that the norm of the vector will just equal the square root of the dot product. And that's why we choose L2. Because if it was L3, then that's not the case. It has to be the cubed root of the dot product. But if it's the square root of the dot product, well here we have the squared is squared, also square root. So it's more intuitive to use L2 instead of L3. And that's why we see L2 all the time. So I guess that's it for this video. We went over the L2 metric space. What LP means. I kind of lied about the quantum mechanics. But for quantum mechanics, well, actually, I guess we can go over what that is. So this is a bit of quantum mechanics, but we know that the wave function, the state vector, is a linear combination of the general one, the superimposed one, can be written as a linear combination of the eigenstates. There's an implied summation here, by the way. I'm too lazy to write. The norm of this, like the length of this vector, this norm, if we operate under the L2 Hilbert space, right, the norm is going to be the, wait, what is it called again? The norm is going, yeah, okay. So, for vectors, the norm of a vector under L2, that's just going to be the square root of, of VP. So it's going to be square root of, like, V, let's say N, P, or 2, really. So it's a square root of this summation, of the value of, Vn squared. That's what the norm is in L2. So the norm of a quantum mechanical state vector in L2, that's going to be the square root. And these are the vector components, right? And the vector components are the Fourier components. So you have the square root of this series, or sorry, not series, this, well, sum series, of the sum over here, you have Cn squared, but well, here you have a complex. This is kind of where it comes in. You have a complex L2 space. So it's not the modulus squared of a complex number will be the complex conjugate. You may have learned that from function analysis classes earlier, but so it's that. And yeah, that's it. That's the norm. And if you guys didn't know this, quantum mechanics are the norm of a state vector should be 1. For physical systems, this norm should be 1. It's just because probability has to all kind of add up to 100%, which is just 1. But yes, our norm does have to be 1. So this would imply that this summation over here has to be 1. These guys all have to be 1. It makes sense then, this because the reason is because the probability of obtaining a certain state of getting Cn, the probability is going to be Cn. So that's for one of them. So it makes intuitive sense how you'd have to add how all of this, for some particular value. It makes sense how if we add up all of these, it should be 1. It's just there should be a 100% probability of getting some value. So that's why it has to be 1. And this implies that our vectors, the norm of our vector, is going to be 1. So that's an application of the complex L2 space in quantum mechanics. That's why we say that, vectors in quantum mechanics, they're in L2. And instead, if it was in L3, this would have to be the cubed root instead for the normal of our vector. This could still be 1, but we'd say it's the cubed root, which is not kind of messy. So we usually just choose L2 for our state vector. So yeah, that's the LP sigma space. I'll be covering the L2 function space in a future video. That's where a lot of the cool stuff happens, because we can talk about nearness of 2 functions in measure theory and stuff. So yeah, it's pretty cool. Thank you guys for watching this video. Excuse the noise intrusions. That was my mother that came in 20 times. But yeah, other than that, guys, I hope you guys really enjoyed this video. And yeah, have a great day. If you guys have any suggestions, suggestions for me, or any questions about me or anything, you guys can feel free to ask them in the comments below. And yes, yeah, have an amazing, splendid, spectacular, fantastic, futuristic day. Bye.